Hello students, welcome to the IR spectroscopy class again. Today we are going to discuss a few more factors that affects the vibrational frequencies as well as the shape and the position of the bands that corresponds to these vibrational frequencies in an IR spectrum. Okay, we have already discussed the symmetry factor, the molecular symmetry factor, the mechanical coupling factor, and Fermi resonance, which is a special case of mechanical coupling. And the next factor we are going to discuss is hydrogen bonding, both intramolecular and intermolecular hydrogen bonding, and how uh, this hydrogen bonding processes affects the shape and position of the IR bands in an IR spectrum. So usually what happens is, say for example, if you consider the case of intramolecular hydrogen bonding in a molecule itself, such as this one, okay, you can see that this typical molecule has got a carbonyl here, and the stretching vibrational frequency of the carbonyl functional group is almost something like 1724 centimeter inverse. But whereas when you have an OH hydroxyl functional group at the ortho position on this phenyl ring, there could be a possibility, a chance of having intramolecular hydrogen bonding between the hydrogen of the OH functional group and the oxygen of the carbonyl functional group here. So essentially, oxygen is an electronegative atom, whereas hydrogen is an electropositive atom. So while the hydrogen making an intramolecular hydrogen bond with the oxygen atom here, so what happens is the hydrogen bonding process, or the hydrogen bonding formation process, requires the electron density on the carbonyl pi bond to be pulled towards this oxygen. Okay, so this reduces the force constant or the bond order of the carbon oxygen pi bond. Okay, so from our famous formula, the lesser the force constant, the lesser would be the vibrational frequency. So since the force constant is being reduced as a reason or as a result of the hydrogen bonding between the carbonyl oxygen and the proton or the hydrogen or the OH functional group here, the vibrational frequency will be getting reduced compared to the vibrational frequency of an unperturbed carbonyl from for here in the first molecule. This is the hydrogen bonding reduces the carbon oxygen pi bond vibration stretching frequency. So the take home message is that as long as we have a favorable situation for an intramolecular hydrogen bonding in a molecule, then this hydrogen bonding process can reduce the vibrational frequency of a typical bond connected to a particular atom, such as the oxygen, carbonyl oxygen here, that is being bound to the proton through hydrogen bonding. Okay, so this could be defined as a typical trend. Whereas if you go on to the case of intermolecular hydrogen bonding that happens between molecules, then usually intermolecular hydrogen bonding not only affects the vibrational frequency or affects the position of the vibrational bands in the IR spectrum, the intermolecular hydrogen bonding changes the shape of the IR bands as well. Okay, so this is due to the fact that intermolecular hydrogen bonding would be occurring between molecules in a sample to different extents. The strength or the extent of intermolecular hydrogen bonding between any two molecules in a sample could vary from molecules to molecules. So since the strength of hydrogen bonding could vary among molecules, this variation could result in different force constants for bonds that are getting involved in intermolecular hydrogen bonding. Okay, so since there, due to this fact, due to the variation in the force constants of the bonds throughout the sample, uh, then each of the molecule could be undergoing vibrational motion at various frequencies. Okay, so we will be seeing a spectrum which is a collection of all these various bond vibrational frequencies. Okay, so this could be an effect that could happen in intermolecular hydrogen bonding. Okay, so again this could happen due to the fact that in molecules such as carboxylic acids, autoprotolysis could be a factor that could occur at effective rates. You know what is autoprotolysis? It's rapid proton exchange between identical molecules. So this autoprotolysis, what it does is the autoprotolysis combined with the effect of intermolecular hydrogen bonding could result in rapid exchange of protons between molecules. Okay, so you cannot really identify a proton as being a part, or a hydrogen atom as being a part of a molecule in the sample. Okay, actually, the proton could be shuttling between two molecules in a sample. Okay, so the proton could belong to one molecule at a time, and the same proton could belong to another molecule after a few moments due to autoprotolysis. Okay, so this changes the vibrational frequencies of, say for example, the OH band of a hydroxylic functional group in a molecule. Okay, in the given sample. So for example, if you consider the spectra of IR spectra of one propanol, the first spectrum shows the spectrum of one propanol taken in the gas phase, and you know that in the gas phase the molecules will be separated by a large magnitude of distance, and there will be hardly any chance for the molecules to interact with each other. So there will not be any chance for the molecules to form hydrogen bonds, okay, effective hydrogen bonds between molecules. So due to the lack of hydrogen bonding, you can consider the OH, the hydroxyl bond, the OH bond, oxygen hydrogen bond, in all the 1-propanol molecules as being in the same chemical environment. Okay, so because there is no hydrogen bonding between the molecules, so the force constant of the OH bond will be the same, or almost be the same, in almost all the 1-propanol molecules. So all the 1-propanol molecules will have the OH vibrations happening at almost the same frequency. So as a result of this, uh, the effect of all the vibrational frequencies, OH vibrational frequencies happening at the vibrational motions happening at the same frequencies, you will be seeing the OH stretching vibration of all the 1-propanol molecules in the gas phase at almost in a close range of frequencies. Okay, so as a result, you will be seeing the OH stretching vibration as a sharp peak in the gas phase IR spectrum. But once the IR spectrum is being taken in a neat liquid state, that means we just take 1-propanol and then take the IR spectrum as it is. Okay, you know that 1-propanol is a liquid at a room temperature. So just take the IR spectrum of 1-propanol as a liquid at room temperature. You'll be seeing the OH stretching band as a broad band compared to the band here, and with the peak of the vibrational frequency being shifted towards a lower frequency. Okay, so this is due to the fact that in neat liquid, the 1-propanol molecules will be in close proximity to make hydrogen bonding with each other. Again, the strength of the extent of hydrogen bonding between each set of 1-propanol molecules will be different throughout the sample, or it could vary throughout the sample. Okay, so this could result in the force constant of the OH bonds in each 1-propanol molecules across the sample having different force constant values. Okay, so since there is a variation of the force constant of the OH bonds in the sample, all the OH bonds in 1-propanol molecules could be oscillating or vibrating at different or various frequencies. So as a result, we'll be seeing the vibrational transitions at in a range covering various frequencies. Okay, and this spectra or spectral peak is actually an envelope of all the vibrational transition frequencies of all the OH bonds in the sample. Okay, again, the spectrum, the peak shifts towards the lower frequency because, again, just like what we have seen in the previous slides, the hydrogen bonding reduces the force constant of the bonds of the atoms that are being involved in hydrogen bond formation. Okay, so the lesser the force constant, the lower is the vibrational frequency. Okay, so the force constant of all the OH bonds in the 1-propanol molecules will be lower compared to the molecules in gas phase. Okay, so this is the reason why this peak shifts towards lower frequency. So again, the spectrum here shows the gas phase infrared spectrum of 1-butanol. Again, you can see the OH stretching frequency somewhere around here, which appears as a sharp single peak because of the fact that there could not be any chance of hydrogen bonding for 1-butanol molecules in gas phase. So the lack of hydrogen bonding makes the OH stretching frequencies to get contained into a small range of frequencies, resulting in a sharp peak here. Again, not all the molecules that could form hydrogen bonds in liquid state gives a broad OH stretching frequency. Say for example, if you take the case of di-tertiary butyl phenol here, the one here, then the neat liquid phase infrared spectra of this molecule gives as a sharp OH stretching vibration. So this is opposite to our expectation, because we in liquid phase we expect a broadened peak which is shifted towards lower frequency compared to its gas phase spectrum. The massive, or the large tertiary butyl functional groups on either side of the OH molecules deeply buries the OH functional group inside them, okay, making it harder for the molecules to come closer to each other and to form hydrogen bonds with each other. Okay, so the lack of hydrogen bonding, or the difficulty of the molecules to form hydrogen bonds, intermolecular hydrogen bonds, makes the OH hydroxyl groups intact, and as a result you will be seeing the OH functional groups to undergo OH stretching frequency at a narrow vibrational frequency range. Okay, again, just like what we have seen in the previous slides, as long as there is an acceptor atom for a hydrogen bond formation process, such as the oxygen of the carbonyl functional group here, we could essentially have a favorable hydrogen bond between the hydrogen and the oxygen. This could lower the force constant or the bond strength of the carbonyl double bond here, making the vibrational frequency of the carbonyl bond, or shifting the vibrational frequency of the carbonyl bond to a lower frequency. Again, in some compounds, intermolecular hydrogen bonding could happen to a greater extent, and the effect of the hydrogen bonding could span towards more than two or three molecules to form higher order self-assembled systems, and this could greatly influence the OH stretching frequency that we see in the IR spectrum of these molecules. For example, this effect is more pronounced in the case of carboxylic acid, organic carboxylic acid molecules. And for example, if you take benzoic acid monomer here, you know that the benzoic acid monomer, it could form hydrogen bonds, intermolecular hydrogen bonds, effectively with other benzoic acid molecules. So one of them is given here, where the OH of the carboxylic acid functional group on one benzoic acid molecule makes a hydrogen bonding with the carbonyl oxygen of the carboxylic benzoic acid of the second benzoic acid, whereas the OH on the second benzoic acid makes a hydrogen bond with the carbonyl oxygen on the first benzoic acid molecule to form a dimer. Okay, so compared to a monomer, you could easily deduce that the OH stretching frequency of these two benzoic acid molecules will be entirely different from the OH stretching frequency of the monomer here. Okay, again, extensive hydrogen bonding could result in the formation of oligomers, whereas In this typical case, which shows the hydrogen bonding pattern between three benzoic acid molecules. Okay, so you can see that the OH stretching frequency or in all these benzoic acid molecules will be slightly different compared to the OH stretching frequency in the dimer system here as well as the monomer system here. So the formation of this dimeric system or oligomeric system by virtue of hydrogen bonding, intermolecular hydrogen bonding between benzoic acid molecules or carboxylic acid systems could result in uh, could result in various force constants for OH functional groups in each benzoic acid systems in the sample, and which could essentially result in various vibrational frequencies for the OH bonds in each of the benzoic acid molecules in the sample. Okay, so as a result, we will be seeing that each of the benzoic acid uh, molecules will be exhibiting the OH stretching frequencies at different frequencies, spanning from something like 2700 centimeter inverse all the way up to almost 3500 centimeter inverse, with some spikes or peaks in between. Okay, and you shall be expecting the monomeric benzoic acid molecule to show its OH stretching frequency at a higher frequency, whereas the dimeric and the oligomeric species will be showing their OH stretching frequencies at a lower frequency because of reduced force constant that arises due to hydrogen bonding between the molecules. So as much as we have seen from the previous slides, we know that hydrogen bonding usually results in a lowering of bond vibrational frequencies. For example, if you consider typical functional group X, H, and X could be any atom such as oxygen, sulfur, etc. So this XH stretching frequency could move to a lower value due to hydrogen bonding, and for the acceptor group, if you call that one as B, such as the carbonyl system, carbonyl oxygen that forms hydrogen bond with the on OH hydrogen. So the stretching frequency of the acceptor group will also be reduced, but to a lesser degree compared to the stretching frequency of the XH bond. Okay, but usually it has been observed that the XH bending vibrational frequency usually shifts towards a higher frequency due to hydrogen bonding. Okay, and this table gives us an estimate of the reduction in frequency due to hydrogen bonding between adjacent OH and carbonyl functional groups in a typical molecule. Okay, so these are the compounds of classes of molecules, and we shall be considering the reduction in vibrational frequencies of OH functional groups and the carbonyl functional groups due to hydrogen bonding in these molecules. So molecules such as 1,2-diols, alpha and beta hydroxyketones, orthochloro and orthoalkoxyphenols. Hydrogen bonding reduces the frequency of OH stretching by a factor less than 100 centimeter inverse, whereas the carbonyl stretching frequency in these molecules will be reduced by a factor of 10 centimeter inverse due to hydrogen bonding. In compounds such as 1,3-diols, some beta hydroxyketones, beta hydroxy amino compounds, hydrogen bonding reduces the OH stretching frequencies to an extent between 100 and 300 centimeter inverse, whereas the carbonyl stretching frequencies in these molecules will be getting reduced by a factor of 50 centimeter inverse in these molecules. Whereas molecules such as orthohydroxyaryl ketones or orthohydroxyaryl acids, orthohydroxyaryl esters, beta diketones, and tropolones, the hydrogen bonding significantly reduces the OH stretching frequency by a factor of 300 centimeter inverse, and the carbonyl stretching frequency could also be significantly reduced by a factor of 100 centimeter inverse. Okay, the next effect that we shall account for that could affect the vibrational frequencies is ring strain. If a molecule which contains a ring, and if the ring is somehow strained, then this could affect the vibrational frequency of a bond that is a part of the ring. So for example, if you consider the stretching vibrations of the C double bond, or that means the carbonyl functional group, in a typical series of rings here, then you shall be able to see that starting from the small sized ring towards large sized rings, the carbonyl vibrational frequency decreases. Okay, so this is in fact is an effect caused by the ring strain as we go from the large size rings towards the smaller size ring. Okay, so what happens here is that as we go from the large size rings towards the small size rings, in order for the carbon carbon sigma bonds, if you identify the carbon carbon sigma bonds, which contains the carbonyl carbon as a middle carbon here, in order for these bonds to form a smaller bond angle as it goes all the way from here larger rings to smaller rings, the uh, the molecule, the carbon atoms, the carbonyl carbon atom which is sp2 hybridized here should become less of sp2 hybridized, because if you consider the hybridization picture here, if you consider this one as a carbonyl carbon and this as the hybrid orbital, the shader orbital here as the hybrid orbital, that forms a sigma bond, the carbon oxygen double bond here. Okay, so this is a sigma bond, that the hybrid orbital that forms a sigma bond in the carbon oxygen double bond here. Then you can think of the other two hybrid orbitals, uh, you know, the two hybrid orbitals that orients at almost 120 degree with respect to each other to form this carbon carbon sigma bonds here. Okay, so if these are the two hybrid orbitals which are at almost 120 degree in a typical system such as the one here, so in order for making the ring smaller, this bond angle, the angle between these two hybrid orbitals should get reduced from 120 degree. So in doing so, if you remember from hybridization theory, a hybrid orbital wave function can be described by linear combination of the atomic wave functions. For an sp2 hybrid orbital, it should be a linear combination of the 2s atomic orbital of carbon, then 2px and 2py atomic orbitals of carbon, right? So in order for making these bonds, the bond angle smaller, then the formation of a smaller bond angle is being largely decided by the orientation or the direction of the 2p orbitals. That means the 2px and 2py orbitals that forms the hybrid orbital here, rather than the 2s orbital, because 2s orbital of carbon is non-directional, it's spherically symmetric. So it is the 2px and 2py orbitals that forms the hybrid orbitals here, decides whether to make the bond angle lesser or greater. Okay, so so that means while making the bond angle lesser, the contribution of 2p orbitals, 2px and 2py orbitals in this hybrid orbitals will be getting increased. Okay, as a result, the 2s electron contribution or the 2s character in this hybrid orbitals will be getting reduced. Okay, so as long as the 2s character on this hybrid orbitals is getting reduced, proportionally the 2s character on this sigma, on this hybrid orbital that forms a sigma bond in the carbonyl system should be getting increased proportionally. Okay, so there should be a proportional increase in the 2s electron density on the hybrid orbital that forms the carbon oxygen sigma bond in the in this typical carbonyl double bond system. Okay, so the carbon, the increase in the 2s electron character in the carbon oxygen sigma bond further increases the force constant of the carbon oxygen sigma bond. Okay, when the bond angle is reduced, and so since the force constant of the carbon oxygen sigma bond increases due to this fact, the frequency, stretching frequency of this carbon oxygen sigma bond will also be getting increased. That's how the carbon oxygen stretching frequency increases as the bond angle the bond angle decreases as we go all the way from right to left on this display of molecules. Okay, so the ring strain here basically compels the molecules to have more s electron density on the carbon oxygen sigma bond, that increases the force constant and that increases the vibrational frequency of the carbon oxygen sigma bond. The next effect that we are going to talk about is the electronic effects, and here we shall be dealing with inductive effect and then the conjugation effect. Okay, so if you were to consider the inductive effect, for example, if you consider the stretching frequency of a carbonyl functional group in a typical organic molecule where the carbon is being connected to a carbon which is being bound to a halogen such as chlorine, bromine, iodine, etc. Okay, and you know that halogens are basically in terms of inductive effect, they are electron withdrawing functional groups. Okay, so these halogens could withdraw the electron density of this sigma bond towards them, which makes this carbon electron deficient. So this makes this typical carbon to withdraw or pull the electron density towards it from this bond system here, and this makes the carbonyl carbon even more electron deficient. The carbonyl carbon is already electron deficient compared to the oxygen here, so this makes this process, the inductive effect, the inductive electron withdrawing effect makes the carbonyl carbon more positive in character. Okay, so this in order to compensate for this effect, the carbon attracts more of the electron density of the carbonyl double bond towards it, making the double bond more stiffened, or making the force constant or the bond order greater. Okay, the force constant greater. So the greater the bond order, the greater is the force constant and greater is the vibrational frequency of the carbonyl bond. Okay, and if you consider replacing the halogen with an inductive electron donating functional group such as an alkylic functional group such as methyl functional group CS3 here, then you know that CS3 will inductively donate the electron density towards this carbon. Okay, and which will make the electron density polarized towards this carbonyl carbon, making the carbonyl carbon electron rich, a little bit more electron rich, and this makes the force constant lesser. Okay, so the lesser the force constant of this carbon oxygen double bond, the lesser will be the vibrational frequency. So this is the effect of electron donating and electron withdrawing inductive functional groups on the stretching frequency of carbonyl functional groups. And the other effect that could lead to a shift in the vibrational frequencies is resonance, which is also an electronic effect. Okay, so for example, if you consider this typical system where the carbonyl carbon is being connected to the carbon of an a double bond system such as an ethylene double bond system. Okay, then oxygen is an more electronegative atom, and you can think of the pi bond electron density as being pulled more towards the oxygen atom here, making the pi electron shift towards this carbon, making a double bond here, and the pi electron shift towards this oxygen, making a negative charge here on the oxygen, which altogether makes a positive charge on the carbon here. Okay, so this one is another resonance structure which happens due to the pi bond system which is in conjugation with the carbonyl system here. Okay, so you can see that this resonance form has got less of double bond character between these two carbons and less of double bond character between this carbon and oxygen. Okay, so this resonance effect makes the force constant of the carbon oxygen bond lesser, making the carbonyl stretching frequency lesser. Okay, so this can be evidently seen here in between these two molecules. If you compare these molecules, you can see that this carbonyl carbon is in conjugation with the phenyl pi electron system here. Okay, so for such a system, the carbonyl stretching frequency is observed at 1684 centimeter inverse, much lesser than the carbonyl stretching frequency in an aliphatic ketone where there is no effect for conjugation. And here the resonance brings down the vibrational frequency of the carbonyl functional group. But here you can see that the carbonyl carbon in this molecule is being separated by the phenyl group by a CS2 in between, and this typical carbon placed between carbonyl carbon and the phenyl ring makes the carbonyl to not be able to interact with the phenyl ring through conjugation. Okay, the lack of conjugation makes the carbon oxygen double bond stiffer and makes the force constant bigger for the carbon oxygen double bond, and therefore the carbon oxygen double bond will resonate at a higher frequency compared to the carbonyl bond in this typical molecule where there is an effect of conjugation. So this effect of conjugation becomes more pronounced as we have more electron donating function groups on the other side of the phenyl system here. For example, if you consider this typical molecule where the carbon is bound to a phenyl ring system, so that the carbonyl double bond can get in touch with the phenyl pi electron system through conjugation. And if X is NS2 here, such as the one shown here, if X is NS2 and we have got this functional group on the other side, then what could happen is the lone pair electron density on nitrogen can be shifted towards this bond, forming double bond here, making a positive charge on the nitrogen. As a result, the double bond on the phenyl ring can be getting shifted, and one double bond shift towards this typical bond here, and that makes the double bond on oxygen, pi electron density on oxygen, the carbonyl double bond to get concentrated on the oxygen here, making a negative charge here. So this essentially makes the charge transfer straight. Okay, so what it does is this conjugation effect or the delocalization of the pi electron system throughout the phenyl ring towards the carbonyl double bond here makes the carbonyl double bond to lose some of its double bond character, making it more or less like a sigma bond or a single sigma bond. Okay, so the bond order will be getting reduced. Since the bond order is lesser, the carbon oxygen vibrational frequency will be lesser. For such a system, the vibrational frequency of the carbonyl functional group is 1677 centimeter inverse, lesser than the vibrational frequency of an aliphatic ketone. And if you replace the NS2 functional group with the CS3, which is a weak inductive electron donating functional group, you should still be able to see this kind of effect, but to a lesser extent compared to the case where you have NS2 functional group, right? So CS3 will still donate the electron density towards the carbonyl oxygen, making this carbon oxygen bond weaker, and still this one happen to oscillate at a lower frequency, but at a slightly greater frequency compared to the case where you have NS2, because NS2 is a much greater electron donor compared to CS3. Okay, whereas halogen such as chlorine is an electron withdrawing functional group. Okay, and NO2 is also a strong electron withdrawing functional group. So let's consider the case where we have NO2 here. So you can see that the functionalization of the phenyl group with the phenyl ring with the NO2 functional group will result in this kind of resonance structure, where the positive charge, we have got a positive charge on the carbon here, whereas double bond can be observed between the nitrogen and carbon here, and the double bond on one of the oxygen will be getting shifted towards the oxygen, making negative charge here, making all to the two negative charges on these two oxygens. And you can see that this resonance structure in any way does not interact with the carbonyl functional group here. Okay, so this resonance structure does not influence the electron density on the carbon oxygen double bond here. Okay, so this double bond stays something like an isolated double bond, or a double bond in a typical aliphatic ketonic system. Okay, so for such a molecule, you can see that the vibrational frequency for the carbonyl oxygen at around 1700 centimeter inverse, pretty close to the carbon oxygen stretching frequency, carbonyl oxygen stretching frequency in, or C double bond stretching frequency in an aliphatic ketonic system. Okay, and chlorine is a not that much as great in terms of electron withdrawing capability compared to NO2. Still, it's an electron withdrawing functional group. So you can see that the chlorine replacing NO2 with the chlorine here results in slightly lesser frequency. Okay, because chlorine, the electron withdrawing capability of chlorine is not as much great as NO2 functional group. Another fact that could affect the vibrational frequency is steric effect, which is not as much important as the other effects, but as long as we have a molecule such as the one here, you can see that the carbonyl system here is in conjugation with the double bond on this phenyl ring system. and this conjugation results in the carbonyl stretching frequency to be observed at 1686 centimeter inverse, less than the vibrational frequency of the carbonyl system in an aliphatic ketone. But you can see that once we have a methyl group at the ortho position here, okay, then what happens is the steric interaction between the methyl group and this typical functional group here makes this typical functional group to come out of the plane of the ring here to a small extent. Okay, this functional groups comes out of the plane of the molecule to a small extent, and this deviation from the planarity, okay, that disrupts the conjugation of the carbon oxygen double bond with the carbon carbon double bond here. So the conjugation is being disrupted. So since the conjugation effect is being reduced due to this disruption, you can see that the bond strength the carbon oxygen double bond strength will increase to a small extent. So the increase in the double bond strength will result in the carbon oxygen double bond to undergo vibration, stretching vibration at a slightly higher frequency compared to the case where the carbonyl functional group is in complete conjugation with the carbon carbon double bond here. Okay, so this is how steric effect affects the vibrational frequency of carbonyl functional groups. So in nutshell, we can conclude that ring strain increases the vibrational frequencies, whereas conjugation decreases the vibrational frequencies of carbonyl functional groups.